Okay, in this example, I want to look at another traditional versus non-traditional approach to conservation of energy with rotation. And in this particular example, we're going to work a little bit backwards, and you're going to see what I mean here in just a moment. But basically, what we're going to do with this particular problem is we have a rod which is fixed in place on the end, and the rod is going to swing down until it's vertically oriented. So it'll look something like this. Okay, and basically what I want to do with this problem, just to keep it a little more straightforward, is to figure out what is the angular velocity of the rod when it reaches that lowest position. So go ahead and attempt this problem on your own right now. Let's see what you would do. How would you go about solving the problem? Okay, so the traditional approach to solving this problem is to treat it like it's entirely rotational. And so we have delta E is equal to 0. So we have delta K rotational plus delta UG is equal to 0. And so we have K final minus K initial plus UG final minus UG initial is equal to 0. And then this is where we have to be a little bit careful. The center of mass is located right here, and whenever this thing swings down to its lowest position, the center of mass is going to be right here. So the distance that the center of mass drops is going to be 1/2 the total length of the rod. And so we got to be careful whenever we set up this part of it. So let's cancel out the stuff that goes away. UG final is going to be 0, because we're going to say at this point y is equal to 0. And K initial, of course, is 0. And so we'll have 1/2 I omega squared is equal to mg y initial. And so rewriting this a little bit, we have 1/2 times. Now, I, for a long, thin rod pivoted about its end, is 1/3 ml squared times omega squared is equal to mg. Now, y initial is going to be this distance, which is 1/2 of L. That's what I'm showing you here, 1/2 of L. So this becomes 1/2 L. So we can go ahead and cancel this 1/2 with this 1/2, and solving for omega, and this mass with this mass, we're going to solve this for omega squared. So omega squared is equal to 3gl over L squared. And of course we get one more L to cancel, and we end up with omega squared is equal to 3g over L. And that's our answer. So that's going to be the traditional approach to solving the problem. But it doesn't really address what happened to K translational, because the center of mass, once again, is in motion. And so now I'm going to work this problem a little bit backwards. Just like I had worked the previous problem, we started with the traditional approach, which uses 1/2 mr squared for the sphere, which means we're using the moment of inertia through the center of, we're using the moment of inertia for which the axis of rotation goes through the center of mass. But in this problem, we didn't do that. We used the moment of inertia for which the axis of rotation goes through its end. And because we did that, we did not have to use K translational. So let's go ahead and solve this problem again in a more non-traditional way. And we're going to use the moment of inertia for which the axis of rotation goes through the center of mass. Okay, so we have delta E is equal to 0. This is going to become And so now we can cancel some things. We know that all the initial kinetic energies are 0. and that the final potential energy is 0. And getting this into the more standard simplified form, we have mg y initial is equal to k final minus k rotational final. Okay, so now we can start making some of our substitutions. We have mg times, now we know that the energy comes from how far the center of mass is displaced, so we're going to say that's 1/2 L is equal to 1/2 mv squared minus 1/2 I omega squared. Okay, so we have mg, well, 1/2 mgl is equal to 1/2 m. Now, we got to be real careful here, because what we have for velocity, we're going to use the bridge equation. We know that v is equal to omega r, but this corresponds to the center of mass. R for the center of mass is 1/2 of L. So this becomes 1/2 m times 1/2 L quantity squared, plus 1/2 I is going to be 1/12 ml squared times omega squared. And remember, we chose 1/12 for I of the rod because this represents the moment of inertia through the center of mass. Okay, so this is ICM right here. All right, so now we can cancel some stuff out. Let's get rid of the 1/2. We can get rid of mass. And we can get rid of 1L. So that I'll get rid of 1 here in a moment. We can get rid of that L. And so now let's expand this out a little bit. We get G is equal to 1/4 L squared, but we got, remember, I didn't cancel it out here quite yet, so let me cancel it now. So we have 1/4 L squared, and I forgot the omega squared, so let me write that in. There's omega squared that goes there. So we have omega squared there, plus 1/12 omega squared L, or L omega squared. All right, so 1/4 becomes 3/12. So we have 3/12 plus 1/12 is 4/12. And 4/12 is the same thing as 1/3. So G is equal to 1/3 L omega squared. And now when I solve it for omega squared, what we get is 3G over L, which is exactly what we got in the previous case, 3G over L. So yeah, this was a very non-traditional approach, and I wouldn't expect you to go through all this extra work, because we have 2 points of contention, or where you could make a mistake quite easily. That's going to be with the velocity here, and then with the moment of inertia for the long thin rod here, because we're used to using the axis, the moment of inertia from the axis of rotation. So this was very unconventional, and I would not expect you to do that, but I wanted to make sure, just how clear it was that that you can do it either way, and that you just have to pay attention to what's happening to the axis of rotation.